So just while we wait for a few more people to come, if you can log into the poll and just let me know roughly how much time the last assignment took you. Okay, so you can go to this address, polyev.com, David Payne 187. Were any of you in the lab on Tuesday? Yeah. How did you find it? Did you finish? Yeah. Okay, we'll just wait one more minute. Okay, we'll get going. So today we're going to cover first the assignment 1 review. So we're going to show you a little bit of the statistics on how people did. You should have got your marks back by now. I think today they were released. So if you haven't checked yet, you can see on Island. Then we're going to go back over differential gain, which we started to cover for the MOSFET differential pair at the end of the last lecture. So we're going to review that. We're going to look at the new topic of differential half circuits. They're meant to make your analysis a little bit easier. And we're going to look at common mode rejection ratio. So this will come up in the next labs as well. And how you derive that, what does it depend on? And then finally we'll finish on the BJT differential pair. So as you can imagine, that's quite similar to the MOSFET differential pair, but there are a few little differences. So we'll go over how we derive the gain and the input limits for that kind of circuit as well. Okay, so a bit of a mixed response on here. I think only one person is basically very quick, less than 1 hour. Everyone else, I guess, struggled with it a bit, okay? I would hope our assignments are probably just under 3 hours, no more than that. So maybe that's to be expected as the first assignment. There's a lot of catching up, especially if you didn't do 275 before. So we'll try to take that on board. Oh, we lost our 1 hour now. And maybe we can make the first one shorter in future years. So yeah, we'll listen to that feedback. Now, this is the summary results of assignment 1. So at the top there we have the average for each question, the average mark of the 90 students I think that submitted. And then we have the distribution here of total marks, okay? So we're just showing this so you get an idea of where you sit. So of course it's anonymous here, you can't see any names. But if you're in that green section, then you're doing okay. So if you're over here, that's a good start. If you're in the red section, probably need to put in a little bit more effort up front to catch up on some of the fundamentals, okay? So have a look at where you are. Especially if you're down here, okay? So, or if you didn't submit at all. These are, these go towards your final grade, so it's important that you put the effort in on the assignments. And I think, typical average mark was 59, so that's not too bad, but we'd hope to push that up to around 65, ideally 70, for the future assignments, okay? And Binesh asked me to tell you, so this assignment was run by Binesh, as you know. He said he'd like people to make more use of the consultation hours if you are struggling, okay? So you can go to see him. I recommend emailing him in advance, and same for when you meet me, email. Ideally say roughly what area you're struggling with, or if there's one particular problem, say, look, I really don't know how to solve this, can I meet you and talk? Or sometimes we'll be able to help in email. So you've seen we put up these videos, these online videos. We can even make a quick video to cover that concept, then you don't have to come in and see us. Saves everybody a bit of travel. So yeah, just use us when you need to. In terms of feedback, so you should all know now your total mark and if you got the answer right or wrong. And I believe you can now see the correct answer, okay? So there's a buffer time after you submit the assignment where you don't know any of the results. Now you get the correct answer. The idea is anything you didn't pass, go back, try it again. You won't get more marks, but for your own learning, try and get that correct answer, okay? If you then struggle, if you really can't find any way that you can get that answer, then you come and speak to us and we'll give you really detailed feedback and help you work through the problem, okay? So we haven't given a detailed step-by-step for each problem because we want you to try and solve it yourself now that you have the right answer, okay? Okay. So we move on to the topic of differential gain. So as you remember from last week, this is our MOS differential amplifier. When we're looking at the small signal operation, that's the regime we're operating in to get the differential gain. We have our inputs of VCM, that's a common mode, which we looked at last week. That's going to both VG1 and VG2. But now we also have a differential input combined with that VCM. That's VID here, okay? That is applied in a complementary fashion. So half of that signal is added to this side, and half of it is subtracted from that side. Okay? So this is your typical operation of a differential amplifier. That's how you want to set up your signal going into it when you can. The VCM there, that common mode, is just that kind of equilibrium state that sets up the transistors to make sure they're both in saturation and everything's operating as normal. So VID is your differential input signal. And as we discussed last week, you can take your output in a single-ended fashion. So just take from Vout1 or Vout2 compared to ground, or you can take it as a differential output, which is what we focus on. Okay, so that's Vout2 minus Vout1. So to analyze this circuit, we can simplify things because we know that our common mode is setting things up so the transistors are in saturation in the region we need them to be. So we can short our power supplies, put that to ground, and we can remove our current source, if you remember from here. And we have a simpler circuit to analyze. And we've removed our VCM because the purpose of that was just to get us into this equilibrium state. So here you can see the transistors are still biased with half of the current going to each side due to the symmetry of the circuit. And we discussed last week as well the virtual ground condition. So that's, you get a 0 volts at the source, and I showed a kind of quick derivation for that to prove it. Remember, that's only valid if you have your output, your differential input, applied in a complementary way. Okay, so plus half on one side, minus half on the other. That's the condition you need to get this virtual ground state, which means this source, this common source, is stuck at 0. It can't really move beyond there as long as the rest of the circuit stays in its typical conditions. Okay, so under this condition, the drain currents are going to be proportional to VGS, and that's going to be related by the transconductance GM. Okay, so this is a standard equation for your MOSFETs. That should be familiar. Okay, in this case, 2ID is going to be equal to our total current I. So the complementary current signals at our drain give rise to these output voltages. So you can see on the Vout1 we have the negative because we have the current flowing down. Vout2, current's flowing up, we have a positive. So you can just take those outputs single-ended, or we can get our differential output. So that will be VOD, which is just VO2 minus VO1. Okay, because you can see that it essentially just removes that, the divide by 2 out of here. Okay, so now if we're looking for a differential gain, that is just simply our output divided by our input. We have the VID term there already, so we just put that onto the other side on the bottom. And we have this expression, which just equals GMRD. Okay, so that's our small signal operation gain, GM times the drain resistor. Yep. And GM is 2ID over VOV. Okay. And remember, if you need to calculate that overdrive voltage VOV, that can be done from the equations we looked at last week. We'll go through that one again today, but that's based on the common mode condition with the current being split across the two. So based on a current of I divided by 2 on each side. Okay, so that was just to review the end of the last lecture. So now we're going to look at differential half circuits. So when we have a symmetrical amplifier fed by this complementary VID, so balanced input, we can study the circuit by looking at just one half of it. So we do the simplifications as before. You can see that we have the power supply grounded, just like before. We assume that the transistors in saturation. But we can also just ground the source terminal, because that's got our virtual ground, okay? So we have perfect symmetry. We can just look at one half of the circuit. And you can see this is now a much simpler circuit to analyze, right? And you would have done this in some of the work with Binish, like looking at these simple transistor amplifiers. No, not for this. So this is just the differential half circuit. So we'll look at the common mode half circuit later. So that can be considered too, but in this case we're just starting with the differential half circuit. Okay? So no VCM in this case. So given this full circuit here on the left, can we work out the gain? So first thing to do is to convert this to a differential half circuit. You can see in this case, in this example, this is a more specific example, we have VCM plus our differential, okay? But we're interested in the differential output in this example. So therefore, in our half circuit, we just look at the differential, okay? VID over 2. You can see our RD is the same. We've grounded the VDD as before. We don't go straight to ground because in this particular example, we've added a RS, okay? So we now keep that RS and then go to ground, because this point here would still have to be 0 volts due to the symmetry as before, okay? But don't forget the RS. And then the other thing to note here is that our load resistor, here RL, here RL divided by 2, okay? And that's because if you look at the symmetry of this circuit, so we take that line of symmetry, we're cutting right through that resistor, okay? So we're just going to split it. And of course we could redraw that circuit with 2 resistors instead, each one being RL over 2. That would give the same circuit, same response. And that's what we've done on the right when we take that half, okay? So we take a differential half circuit, and to do analysis on that, so we're interested in finding out the voltage gain, we can look at equivalent circuits. Okay, so these you should be familiar with a little bit from last lecture and from Binish's lectures. If you're not familiar with how to do the equivalent circuits and what the parameters mean, definitely something to go back and look into, okay? And I think Binish has some videos on this. There's a lot of information online as well, okay? Yep. Huh? Is this the slides online? Yeah, I've changed it. Yep. Okay, so sorry, there were some errors. So I updated this version of the slides. The way I do all of these, I have some initial slides online so you can kind of follow through. But then I always put an updated version after the lecture, which has my notes and the answers to the questions we ask, okay? So, yeah, apologies if there's some differences between the two versions. Of course, you can follow through on here. Okay, so that's our equivalent. We have a GM VGS, and note that I've included the full model here, which includes R out. But actually, for most of the analysis today, we'll neglect that, okay? We'll assume it's large enough that we can not worry about R out, because it will complicate the equations and make very little difference to the answer. But that won't always be the case, so just something to bear in mind. But the simpler model just excludes this part, and you just have your GM VGS, okay? And remember that the input is now not between the gate and the source. It's got the RS resistor involved there as well. So let's analyze this circuit. First we can say that our output minus VOD over 2, so remember we're only looking at one half the circuit, so we only have half of that differential output, okay? In this case, the negative half, the minus VOD over 2. That is equal to GM VGS, that's this current, And we find the voltage here by just getting the resistors in parallel, RD and RL over 2, then we get the voltage drop across those resistors in parallel by timesing that by the current GM/VGS. Okay? So very simple to get that output expression once we have the equivalent circuit in there. So then we need also an expression for our actual input. So VID over 2, according to our model, is going to be this voltage drop, VGS, plus the voltage drop across RS. Okay, so the total drop from input down to ground. And that's going to be, again, GM/VGS, which is the current going through RS. Okay? So now we have our output and our input. So to get the gain, we just divide one by the other. Okay? And of course, in this case, the divide by 2, we can get rid of that. That's cancelled out. And we get this expression over on the right, which you can see can be simplified a little bit more by dividing through by GM, well, by the bottom expression. So that's our expression for our difference mode gain. And you can imagine how this expression will simplify if we take assumptions such as GM being much smaller than RS, and things like that. You can remove parameters and end up with a expression of GM/RD, which was our previous gain expression. Okay, so with this circuit was now a little bit more complicated. We added in some resistors. We've got the RS, the RL. That changed our gain, but if we make assumptions about the size of those, we can kind of neglect them and get back to our original gain. That's always a good reality check to do, to make sure you've got the right expression if you're deriving it yourself. Okay? Okay, so a question for you guys. With a MOS differential amplifier operating at a total current of 0.8 milliamps, you've got some transistor characteristics here. What's the value of GM? So 2 minutes, if you go online and vote. So you'll need a couple of equations. One of them is going to come up as a hint in a few seconds, but these are the sort of equations. These ones that come up as hints, those are ones you should know, and try to commit to memory. Okay? Okay, there's one hint come up. So the overdrive voltage. Any more answers? Okay, so let's first calculate our VOV. Oh, we got another answer in. So that's going to be our total current, 0.8 milliamps, divided by 0.02 all square rooted, so that 0.02 is just 100 times the 0.2 milliamps per volt squared. So that part's going to equal 0.2 volts. Yep. Now the other equation you need, which hopefully you're familiar with, is GM equals 2ID over VOV. Yeah, it's not letting me write it. Something's up with the pen. Okay, 2ID is just I. Yep. So that becomes 0.8 milliamps divided by 0.2 volts. Or divided by 0.2, 4 milliamps per volt. Okay, so most of you got it right. I think just 1 on the 2 milliamps there, potentially half the I instead of using 2ID equal to I. Okay. So now we look at the common mode half circuit. So before we looked at how you convert that circuit if you're interested in the differential output. But what if you're interested in the common mode output? There are a few differences. So you can see we have a similar circuit to before. We still have a load resistor across the output. We still have a source resistor, but we've also added a resistance to the current source, okay? So it's no longer approximating a perfectly ideal current source. So what does that become as a differential half circuit? Well, we keep our RD as before. We now have still have our source resistor, and we have 2 RSS at the bottom, and that's simply because, again, we don't have a perfect line of symmetry here. Okay, but you could make this symmetrical by making it 2 resistors in parallel, right? So again, same circuit. Now we take 1/2 after we've removed that current source, and we'll have a 2 RSS. Okay, so that's the situation there. And the other difference is that the load resistor doesn't appear in the half circuit. Okay, that's because for common mode these are equal, these output voltages, as you know, we've shown that a few times, which means there's going to be no current going through that load resistor. Okay, so it's not going to have any effect. We can ignore it. Okay, so that's our common mode half circuit for this example. So again, going to our equivalent circuit models. Again, we have our GM/VGS, we have R out, and we can do some analysis on this. So V out 1 in this case is going to be minus the GM/VGS times RD. Again, we're neglecting R out, assuming it's very large in this case, and that's going to be the same result for V out 2. Our input, VCM, it's going to be this voltage, VGS, plus the GM/VGS, which is the current across these 2 resistors, RS and 2 RSS. Okay? Which means common mode gain, if we're looking for differential output, that's V out 2 minus V out 1. It's going to be on top of this expression, but that doesn't matter because the top part of it is 0, so output is 0. Okay? As we know, as we expect with an ideal circuit, common mode input, we're going to have a 0 differential gain. So all these expressions we did last week for the full circuit, but now we can get the same result with this half circuit, which is going to make life much easier if you get a complex circuit to analyze. Now, what if there's a slight mismatch in the drain resistors? So up till now, we're looking at perfectly matched circuits. That's not a realistic situation. You all know resistors have a tolerance band, like you can work out the tolerance. There's some error between them. And there's also going to be error in the transconductance of your transistors. Probably less so because they're made in a single IC, like next to each other. So they're a very, very robust process. So they're going to be closely matched. RD might not. So if we look at that case where RD is not matched, then we have basically two circuits. One where the V out is as before, minus GM, VGS, RD. And the other one where we have RD plus some change, some delta RD. Okay, that's the difference between the two resistors. Of course, these are interchangeable. You could have your V out 1 being the delta RD or the V out 2. So now when we subtract one from the other, of course, we no longer have 0 as our result. We have minus GM, VGS, delta RD. If we plug that into our equation from before, so we already derived this part last time, but we could ignore it because we had a 0 on top. Now we don't have the 0 on top. We put in our minus GM, VGS, delta RD, and we get this expression. Okay? So now you can see what the common mode gain relies on if your resistors are mismatched. Okay? So of course there's a dependency on that mismatch. You want to minimize that if you want to get your gain to be 0. Okay? So we're aiming for a 0 common mode gain. If that's 0, it goes to 0 again. We also want to maximize those resistance values, minimize GM, and there's other ways so that these all have an impact on our common mode gain that we don't want to be above 0. And just a quick note, if the mismatch is more than minute, so a very small mismatch, this is a good enough approximation. If it gets bigger, then that assumption we made earlier that we could ignore RL for the common mode case, that becomes invalid because our circuit is not perfectly symmetrical. There will be some current flowing through RL. We have to add that into the analysis. Okay, but that gets quite complicated. The equations will get bigger, and we won't go through that today, but it's something to consider. Okay. So next we'll look at the common mode rejection ratio. So we covered kind of what that means at the beginning of the last lecture. Now we're going to look at how we can actually calculate it. And we know that common mode rejection ratio ideally is going to be infinite. Okay, you want to reject all common mode signal, attenuated down to nothing. So how do we get that from our equivalent circuit? Well, the CMRR is just the differential gain divided by the common mode gain. Okay? So we previously derived these expressions, and this is for the case, of course, where we have a delta RD, okay? Because otherwise that common mode gain is 0, CMMR is infinity, as we want it to be. So it's not a problem, we can not worry about it, but as soon as we have that mismatch, now we're interested in how that affects our CMRR, okay? So we have that expression. If RS is very small, which is a reasonable assumption, then we can simplify our expression a little bit there. And we can rearrange into this expression, a little bit easier to handle. So that's just by multiplying through by GM and by 1 plus 2R SS. So the smaller the mismatch, the greater the CMRR, okay? Which is a good thing. We want high CMRR, high common mode rejection ratio. And this mismatch, delta RD, you might notice that we haven't included it in the part of our differential gain. We just used that old equation for that. That's because if you do that, you'll realize it has a very small impact on the differential gain. So that change in RD, that mismatch, mostly affects the common mode gain. So we neglect it when we look at the differential gain and just include it on the bottom here. That will give us a good enough answer to a good enough accuracy. And don't forget the CMRR is usually expressed in decibels. Okay, so 20 log 10 of this number. Of course, if we ask you a question, we'll tell you how we want that expressed. So we might ask for it in volts per volt or decibels or. So you can do a similar analysis to look at the mismatch in transconductance, okay? We won't go through that one today. That's something you can try at home, so you can see how that affects the equations if your transistors are not perfectly matched, okay? And don't forget, using these models will help you to analyze those circuits. You have the choice of the hybrid pi or the T model. Both of them can get you to the correct result. Okay, so that's pretty much everything covered for the MOSFET differential pair. Okay, and that's what you've been working on, well, will be working on in this week's lab, and some of you already did that yesterday. And in fact, next week's lab will also be MOSFET differential pair focused, but in that one you'll start to actually build it and expand on the circuit a little bit. The following week we'll look at the BJT in the lab, so we're going to cover the theory for that now. This is our last lecture on differential amplifiers before Binesh takes over on the next topic next week. So the BJT differential amplifier, you can see up here, very similar circuit to your MOSFET differential amplifier, and it will give you a very similar result, but the way we derive those equations will vary a little bit. One key point to note is the region that you want these BJTs to be operating in. So as you should know from your previous lectures with Binesh, for amplification, the BJT needs to be in what region? Does anyone know? Yep, excellent, active region. So that's a distinction from, at least in terminology, from the MOSFETs, which you need to be in saturation region, okay? So don't mix those up. That could be quite disastrous. So here we have a simple example circuit, VB1 and VB2 going in. Again, we have an ideal current source, and we have some output resistors. So yeah, essential that it remains in the active region. So we'll first look at the common mode. So as we did for the MOSFET differential pair. So this is where we have that same common mode signal going to both of the transistors. Base terminal on both. Now here we have, as before, through the symmetry of the circuit, you can see our current source is split through both sides. So we can say that our IE1 is equal to IE2, which is equal to I over 2. Okay, so that's obvious from the symmetry right at the start. We can see that VE, that's at the voltage down here, is going to be equal to the VCM base input here minus the VBE. And for transistors in the active region, the VBE is going to be approximately 0.7 volts. Okay? So that gets us to that result there, VCM minus 0.7. Okay, so under our normal operation, we can assume that 0.7, which is another difference between this case and the MOSFET, okay? And our VC, this point, that's going to equal our VCC minus the drop across that resistor, which will be alpha I divided by 2 RC, because we know our emitter current is I divided by 2, and we know from our simple transistor equations that that means our collector will be alpha times IE. Yep. So that's again just from the standard operation of a BJT in the active region. So yeah, remember. Okay, and as we might expect, our V out is going to equal 0, our differential output, because we have the exact same on our V outs for both our collector things. So just like with the MOSFETs, common mode signal input, 0 output, assuming we have everything ideal in our circuit. What about for the differential mode? So we'll start by looking at just the case where we ground one terminal. Again, we did this for the MOSFETs, and then we have a small input signal, VI. So this will change the currents, okay? As you know, now we have a small signal here. We're going to increase this emitter current by delta I, decrease the one on the right by the same amount of current. So that's going to change our output. Okay. So now we have an actual differential output. Again, exactly what we want from a differential amplifier. No response to common mode and an amplification response to difference mode. So let's look at this quick example. So we want to find the voltages of this amplifier, VC1, VC2, and VE. So we start by assuming Q2 is in the active region, and we start the analysis from there. So for Q2, we know that in this case our VBE, so this voltage is going to equal 0 minus the emitter voltage VE. We know that VE is going to equal minus 5 plus I times the 1K. So that's the minus 5 down the bottom here, plus the drop across this 1K resistor. Yep. So we can say VBE is equal to 5 minus . And we get an expression for the current, okay, through just rearranging those equations. So if we assume this active mode region, we can take VBE to be 0.7, okay? If we do that, then we get 4.3 milliamps. And we can tell from up here, we'd also get the fact that our VE is going to equal minus 0.7. Okay, so therefore we have our VE. Now we look at Q2. So for Q2, VBE is going to equal minus 0.5, in this case plus 0.7, 0.2. So that means it's not in the active region. It's going to be cut off. Okay? Q2 is in cutoff. That means all of the current will be going through one side. Therefore, we can work out from there VC1 is going to equal 5 volts. VC2 is going to equal 5 minus, because we have all of the current going through this side, so we'll have, in this case, 4.3, 0.7. Okay? So that's because we have all that current going through our 1K resistor here. So that drops our voltage of VC2. Yep.
You said for Q2 the first time and for Q2 the second time. Is that also for Q1?
Oh, sorry. Q1 is the second one, yep. Sorry. Let's see if I can delete that. Yeah, Q1 is in cutoff, Q2 is working. If you try that the other way around, if we start that assumption that that Q1 is operating and has a VBE of 0.7, you'll find it doesn't match up when you then get to the other one. It forces Q2 to also be active, which in turn it's a paradox. Q1 can't be active, okay? That goes back to kind of like when we looked at diodes in 275 for anyone that was in that one. You sometimes have to make some assumptions at the beginning of your analysis and see if that logically works out. And if it doesn't, then try a different assumption, okay? Until you get to a steady state that works without any contradictions amongst the circuit. So in this case, I knew that it was Q2 that was in the active region, so we started with that. But if you did start with the other one, you'd think, okay, this is unsolvable. I'll try the other assumption. Okay, so what about the voltage limits? Do you remember we did this for the MOSFET differential pair? So there's going to be some common mode limits over which this amplifier will operate as we want it to. The maximum common mode voltage is going to be limited by the BJT leaving the active mode, in this case entering the saturation region. So if you remember from MOSFETs, it was limited by the requirement to stay in the saturation region. So that's quite simple. We know that as we're entering the saturation region, in that case, VBC is equal to 0.4, so that's VB minus VC equals 0.4. In this case, our VB is our VCM. So we have simply this expression. And it's approximate because that 0.4 is an approximate value. Okay? And that's from, again, should know from the previous lectures, the VB being 0.7, the VBC 0.4. These are all just the standard voltages for switching regions. So if that's unfamiliar to you, go back and look at the BJT work and go through some of those videos, and that will come back to you. So once we have that expression, we just need the expression for VC, which, as before, is our supply minus the drop across RC. So that's VCC minus alpha I over 2 RC, now plus 0.4. So that's our equation for the maximum common mode input. If we go beyond that, the transistor won't be in the active region anymore, and it won't behave as we want it to. as with the MOSFETs, the minimum is going to be defined by the voltage needed across the current source. Okay, so you have some voltage VCS required in order for this current source to keep maintaining the current that you need. So same as with the MOSFET analysis, we can show that to be minus VE plus VCS plus VBE. Okay, so that's your common mode limits to your BJT differential amplifier. So here's a question for everybody. What is the VCM min of this differential amplifier, so the minimum value? And you've given some parameters for that circuit there. Power supplies 2.5, current source 0.4 milliamps. And if you've forgotten the equation and you don't have the slides, then that should pop up in a second. There you go, that's the VCM min equation. Should be very easy to get the answer once that's in front of you. Okay. So a little bit of a mixed response, some minus 1.5, some minus 1.7. So let's have a look at this. So our VCM min in this case is just going to be minus 2.5 plus 0.3 plus 0.7. Okay, 0.3 is our VCS, that's the voltage our ideal source needed, or in this case not so ideal. VBE is our standard for inactive mode VBE. Should be minus 1.5. Okay. What about the VCM max? So that's just VC plus the 0.4. We have our expression for VC here. So that would be 2.5 minus, we'd assume alpha equal to 1. And we get to 1.9 volts. Okay? Make sense to everybody?
Where's alpha?
Alpha, so that's a term in this case we didn't define. It's always very close to 1. Again, you should know that there's expressions for alpha from the BJT fundamentals. If it's not given to you, assume it's 1. Okay? Usually we would put the number of alpha in the equation. It might be 0.99, 0.98. But yeah, it's also typically assumed to be 1. That's your relationship between your emitter and current, emitter and collector currents. Okay, we have a few more people turn up, so I'm just going to go back quickly. Hopefully this shows up to this poll. So if you didn't vote earlier, can you just give us an idea of how long it took you to do assignment 1? So I think we got 5 or 6 more people at least. So far, everyone took quite a while on it. I'll just give you a minute to update any answers there. Okay. And again, for those of you that weren't present at the start of the lecture, so we did hold up for a bit. I know some people can't get here on time. This was the assignment marks summary. So just assess where you fall. You should have your marks available now. This slide will go online after the lecture as well, so you'll be able to see. If you're in the green region, things are going pretty well. Especially if you're scoring in the 80s and above, that's great. Almost, I think we only have one person score 100%. If you're in that red region, that means you've got to put in a bit more effort up front, okay? You're going to need to look over some of those intro videos. Make use of Binesh's consultation time. If you struggle with the differential amplifier parts, but for the next assignment, make use of my consultation time. And yeah, hopefully we can improve on that. Also, if you're struggling with concepts, you can, as I said, email us, but you can also make a forum post, okay? You guys can help each other out. Someone can post on the forum, say, I really don't understand this. And maybe, because me and Binesh are both busy, another student might answer before we even get to it. So, you know, we'd love to see a bit of community spirit helping each other with the understanding. All right, let's get back to it. So what about the full transfer characteristics? Hopefully you remember we looked at this for the MOSFETs. So this is going to be, how does our current, in this case IC over total I, but effectively IC, change with our differential input, okay? So this is going to be defined by the fundamental BJT equations, right? So hopefully they look a bit familiar to you. We have an equation for IE1, and an equation for IE2. Same equation, except this one has VB1 in it, and this one has VB2, okay? And you should all be familiar with the thermal voltage VT. And we normally approximate that to be 25 millivolts at room temperature. So combining those equations, which is one divided by the other, we can get this exponential in the form VB1 minus VB2. For manipulation of that, with the constraint that our currents must add up to equal the total current available, we can get these expressions for IE1 and IE2. So these depend on the VID over VT, VID being the difference between those base terminals, okay? So you can go through that yourself, check that it makes sense. And you can see from this plot, there's a linear region, but it very quickly gets non-linear, okay? So we're mostly interested in, for amplification, we want things to be linear. We're going to stay within this region. And you can see that 4 times the thermal voltage is enough to pretty much cut off your transistor in one direction, okay? That's about 100 millivolts. So very small changes in input differential voltage are going to make large changes in current. If we want to stay in this linear region, then we're going to keep our differential input to around 0.5 VT, so half the thermal voltage. It's just 12.5 millivolts either side, okay? That way you know you're maintaining linear amplification. So this is much less than the MOSFET input range, which we calculated before. But the advantage is it will be very fast to respond, okay? Because those tiny changes in your input will quickly change to a big change in your current and then big change in your output voltage. Okay, so these can be used as fast current switches. Okay, so another class exercise. For the BJT differential pair shown here, what's the value of the differential input signal required to get IE1 to equal 0.99 of I? And you already have a hint right there on the screen. This one shouldn't be too hard. It's a bit of calculating, that's why you've got 3 minutes for this. But everything's in that expression down in the bottom left there. We're trying to get the value of VID. A bit of a mixture. Yeah, if you didn't bring a calculator, definitely helps to bring a calculator to these. Won't all be very easy to do by hand, especially when we've got exponentials in there. Okay, so it looks like people narrowed in towards 2 answers, or 1. 115 millivolts is the correct answer. We'll go through that now. So just using this expression here. Now we know we want IE1 to equal 0.99I. So we can say straight away the left side of that is 0.99I. equal to I over 1 plus. Okay, you can see that i's cancel out. Just divide by I both sides. And we can then rearrange by flipping the equation. And then if we, then we subtract 1 from both sides. So now we have 1 over 99. Then we take the log and we can times by Vt. Okay.
Excuse me, but how can we derive that hint?
The hint?
Yeah.
So that was in the previous slide, which I showed you the step-by-step on the transfer function. Based on the transistor equations for the emitter current. Yep. Have you got the slides there?
Yeah.
I can go back to it. This one here. So that's these. Oh. These expressions here at the bottom left. Yep. So they come from the ones at the top left, which are the standard equations for emitter current. Okay, those are the ones you need to be familiar with for your BJT. Hopefully Binesh covered that, and then you can derive all the rest. Okay.
Do we get that in the formula sheet at the end of the semester?
We haven't made the formula sheet yet, so I don't know. It would depend what questions we put out. Probably yes. Yep. So we're not too worried about making you commit all of this stuff to memory. Some of the simpler relations, like alpha and beta, we might not put on there because that's stuff that you really should know. Probably anything that gets a bit more complex, has exponentials in it, we'll give you on the formula sheet. Okay, and then you just got to know when to use it. Okay. Okay. So the small signal operation of your amplifier is kind of summarized here. We won't go through all of this in detail today, but you can work through it yourself, or if you have access to the book, which is in the library, it's available in the Cedra book, page 619, small signal operations. They go through the whole derivation of all of these formulas. It's quite straightforward. But we're going to use this to get to the differential gain. So we have our small signal approximation circuit. There we have our collector voltages, okay, just from these expressions. You can see where they're coming from, so that's your VCC up here minus the drop across here. And then we have this minus GMRC VID over 2. That's our response to the differential input, okay, the change in current. For VC2, again with our differential input, the only difference now is we have a plus instead of a minus. So of course if we do the differential output, VC2 minus VC1, then we're going to get, in this case it will just cancel out the 2. Okay, GMRC VID, everything else cancels out. And then if we want the gain, then that's VOD over ID, so GMRC. Okay? So if you remember right back to the beginning of this one when we covered the small signal for the MOSFET differential pair, same equation, right? Except RC, RD, but that's our output resistor. So you can do this with the derivation in the book, or you can go through yourself by replacing these transistors with their equivalent circuits, which we've been doing it like for the half circuits earlier. So that's all stuff I'd encourage you to do in your own time. Redraw these circuits, see if you can get to all the same expressions. There's many different ways to get to the same number, basically the same expression. So just to go back over those models, and I think Binesh would have covered these in more detail. I think he has videos on these, so they're always good to go through. So you have the T model or the hybrid pi model, and different versions of those. So select the most appropriate one, given the requirements that you have, like what are you looking for, and put that into your circuit. And don't forget, they're a bit small here, but these expressions, how do these terms in the model correspond to actual circuit terms, collector currents, thermal voltage. This emitter resistance RE is your thermal voltage divided by the emitter current. Okay, those are all standard terms, they're not going to change, but you should be familiar with those. Again, back to the question on the formula sheet, I'm not sure which ones we'll put on there, but probably, I know in 275 I think we'd supplied these models as part of the sheet. We will give you the sheet in advance, okay? So you'll know what is missing or what not. Don't take that as a clue to the kind of exam questions you're going to get though, okay? It would just be the basic formulas that we don't want you to spend too long memorizing. We know that in real life you can Google these straight away. In a job you're not going to need to know it all at the top of your head, but you will learn it that way. So yeah. So another little bit of revision, just stepping through how GM is derived. So you notice that GM is in both of these models, IC over VT. Yep. So I won't spend too long on this, but we can step through the expressions. So VBE, that's our total, like our instantaneous VBE, the small and large signal, okay? So large VBE plus small VBE is this one. So you see the small V, but the large B and E. So using our expressions for current, we can get to our IC is equal to this one. So this is your VBE from up here. This is our total IC. And that equals the saturation current times our large VBE plus our small VBE over VT. So these are just the fundamentals, the fundamental equations. That can be split up just by splitting the exponentials. So you see that this term on the left is equivalent to the large IC. It's got the large VBE. So we can separate that one out and just call that IC. We can use the exponential approximation to simplify that. And then we can just get rid of the brackets. And in this case, we now have our small IC taken out here, just based on small IC. Well, our total IC is equal to big IC plus small IC. So using that, we can get to this expression. From there, we can define GM as equal to IC over VT. So we've just defined that parameter, which allows us to have IC equal to GM VBE. So it's quite a lot to get your head around. It should be in Binesh's lectures, maybe in more detail. But that's the kind of derivation you could be asked in an exam. So be familiar with those steps. The notation is quite tricky, I know, with the small and large and getting it all to be clear. But if it is an exam question, just do your best with that. Even if you have an arrow, if you struggle with small and large C's, you can use your own terminology and define it somewhere else on the page. There's all sorts of tricks like that. So an alternative way of finding the differential gain, so we just looked at that through the approach in the book. We can also just use our equivalent circuits. So in this case, our IE is going to be equal to VID divided by the total resistance seen by that current, so that's 2RE in this case. We know that IC equals alpha IE, so that gives us alpha VID 2RE. And then we get an expression for VC1 minus alpha VID RC, so that's that current IC just going through the resistor RC. We have it grounded here, so it's a negative because it's 0 minus that voltage drop across that resistor. Same for VC2, but in this case positive because the current's going the other way. And VC2 minus VC1, so our differential output, as before, the 2 cancels out because we're just adding them. And we have our gain alpha RC over RE. And if we remember our expressions from our equivalent circuits, GM is equal to alpha over RE. Okay? So that expression, when you plug that in, you get this very familiar AD equals GM RC. Okay? So another way to get through to that gain equation, and you just need to be familiar with converting those terms to get it into the expression you want or the expression that you're asked for. For example, you could be asked to use this model to show this result. Okay? In which case, then you're going to need to remember that step there. Okay? Okay, what about the input resistance? So we can use this model to find that as well. Input resistance is just the input voltage divided by the input current. In this case, input voltage is our VID, just our simple input there, and our input current is IB. So we don't yet know what IB is, so let's look at IE. So that's already, we have an expression for that, which is our voltage across those 2 resistors. We derived that last time, so VID over 2RE. Now we know, again, for our transistor expressions, IB equals IE over beta plus 1. So we can plug that in to get a value for IB. So we have our VID divided by IB. Of course, our VIDs then cancel out. Equation flips, so 2RE beta plus 1. Okay, makes sense? So now we have an expression for the actual input resistance seen looking into the circuit, okay, from the input. So how does that affect the differential gain? So we have our standard BJT differential pair. We've got the equivalent circuits. Now, if we've added an actual, we already have our model RE, but we have an actual emitter resistor now added here. How will that affect the gain? So we can go through with the same process as before. The only difference is that instead of just 2RE with the small RE, we now have our big RE as well, this one. So all of our resistance terms in the brackets become 2RE, plus small RE plus big RE. And you can see our gain here becomes small RE plus big RE, so the gain has a dependence on the emitter resistance that you add to that circuit, or that is included in that circuit. And as does our input resistance, that also now will depend on the emitter resistance. Okay, so just identifying those dependencies is pretty key when you're designing a differential amplifier. And what about the differential half circuit? So as before, we have the symmetry of our circuit. So we have a differential input, VID over 2. Symmetry of the circuit means you have a virtual ground, okay, same as before. That means, because if there's a virtual ground there, ground here, RIE can be ignored or neglected when we convert to a half circuit, okay, due to the virtual ground, because there'd be no current going through REE for a differential input. So if we convert that to our our equivalent models, then we can see that our AD is going to be, well, let's look at it. GM, in this case GM V pi, but then that will be divided by the VID V pi at the input. So those will cancel out. We end up with just GM RC in parallel with R out, or if we neglect R out, just GM RC. So differential gain, same as before, through this half circuit analysis, okay? So we can get that result from the full circuit, we can get it from the half circuit, in this case with that REE, which made no difference to the differential gain. But what about the common mode gain? So in this case, we no longer have a virtual ground there. That was a product of the complementary input for the differential gain. So that becomes these half circuits. As before, our line of symmetry is going straight up here, a bit of a dodgy line, but we split those resistors as 2 in parallel of 2 REE, so therefore we have 2 REE on our half circuits. Okay? So yeah, again, typical exam question can be to draw the half circuit, do some analysis, and make sure you understand how these resistances will change. In the differential mode, RE disappears. In the common mode, RE will be double. And as we looked at before for RD, what if there's an imbalance in RC, our collector resistor? So you can see that's a delta RC on one side of the circuit. So if we look at our current terms now, so same as before, we have IE, it's VICM over RE plus, in this case, 2 REE. IC is just alpha times that, which means our output voltage, in this case negative, times the drop of this over this resistor, so 0 minus the drop here, which is this IC term times RC. But on the other side, we have the delta RC included as well. So if we look at our differential output, again, remember we're in the common mode, so typically this would be 0, but now we have this imbalance. And we have this expression. If we look at that in terms of gain, we just divide by that VICM, so it simplifies slightly. And again, very similar to the MOSFET, we can see that the gain in the common mode, which we want to be 0, is going to be very dependent on that change in RC, that mismatch, okay? That completely affects it, and then Assuming that can't be avoided, you have some mismatch, then it's the emitter resistance that will dominate the value there. Okay. So if you were given a mismatched circuit and asked to maximize the gain, assuming you can't change the RC values, then those are the values you need to change, okay? And the CMRR is going to be your differential gain divided by your common mode gain. So that leads to a bit of a big expression, but we can assume that RE, small RE, is much smaller than 2REE, the resistors we actually added. Small RE, remember, is just the RE from the model, the equivalent circuit. And we assume alpha equals 1, and we get a bit of a simpler expression there. And again, you can apply your logic. If you set your RC down to 0, nothing's mismatched, then your CMRR will go to infinity. Okay? You can also, through the same equivalent circuit models we've been looking at, you can see the effects on the common mode input resistance. That's a bit longer, a bit more tedious. We won't go through that here, but it's pretty straightforward, same kind of analysis, so that's another one you can do at home. All right, so let's have a question. Amplifier shown below uses transistors with a beta of 100. What is the input differential resistance, RID? And you already have a big hint up on the screen there. All right, quite a mixture. About half a minute left. It's changing rapidly. You're just playing with your phones at this point. Going in the right direction. It was, no. There we go. All right, stop there. All right, so the correct answer should be 40K, or it's at 40.4K, but yeah, of the ones there, it would be 40K. So I'll go through how we got there. Yeah, now you change it. Perfect. All right, that's the screenshot we'll show. So Let's have a look at that. One second. So we know the equation for RID. We already derived that before. It's on the screen. So we just need to work out what the variables in there are. And beta is given to 100. And the large RE is given to you here, 150 ohms. Yep. So really all you need to work out is the small RE. And again, from those equivalent circuit models, RE1 is going to be equal to RE2 because they have a symmetrical circuit. That's going to be VT over IE. Okay, so simple equation, but it wasn't on the screen. You have to have remembered it. So that's 25 millivolts over IE, which is going to be 0.5 milliamps, because we have 1 milliamp split evenly across our differential pair. Okay, that's our source. So we're going to have I divided by 2 going to each emitter. Yep. So that might be where some people tripped up. And that should be equal to 50 ohms. So then if we plug that into the equation, which we have at the top there, RID is just going to equal 300 plus 100 times 101. That's the beta plus 1 is the 101, and then the resistor value is adding up to give us this, to solve that equation there. Should equal 40.4 kilo ohms. Okay? Now, what about the gain? What's the gain going to be of this circuit? So that, now we have a more complicated circuit. We need to work that out in stages. Okay? So from the signal source to the base inputs, there's going to be a certain gain. That's VID is our actual base input, Vsig is our source. If we're interested in the gain, we can just look at the ratio between the resistances seen in that part of the circuit. Okay, so that's the kind of quickest, easiest way. But you'll need to look at the total resistance. So in this case, that will equal RID divided by RID plus R signal. Now we know RID, we just calculated that to be 40k. Our signal is the total resistance seen from the signal point of view, which is going to be 10k. It's the 5k plus the 5k. So we have 40k over 50. .8 gain, so it's volts per volt. Now, so that's the gain just from between our inputs, basically our signal and our actual base input. So now we also need the gain from our output to our VID. So our output to our transistor input. So that's our I've zoomed in accidentally. VID over VID, okay? So total resistance in our output is going to be 2RC, and our total resistance this would in this case in our emitter And again, we can work these all out from our small signal equivalents, but we won't go through all of that there, but this will be and we have all of these values. Oh, God. We have 50 volts per volt. So now, to get our total gain, we simply multiply the gain of the two stages, okay? Okay, so that one's a bit more complicated. Yep.
I think BCD equal to ampere RC.
Pardon?
For the game, BCD over ID.
VOD, sorry, yep. It's bad writing.
Is equal to ampere RC, right?
Equal to?
Ampere RC, not Joule RC.
Oh, sorry, yes. No, 2RC in this case, sorry, 2RC, because it's our total from the collector. This is 2RC. Yeah. So, this one's a complicated example. I suggest this one's in the book as well. That will go through it a little bit more with a few more steps and explaining a bit more about how we can use these ratios, okay? But the idea is it's the total resistance seen by the collector terminal, so you add them up. We'll leave that one there. So we'll just finish up on active load. So we've talked a lot about the differential output and the advantages of differential output, which there are a few, especially being avoiding noise in your circuit and getting maximum gain, okay? Because as soon as you go to single-ended output, you basically cut your gain in half. But at some point, you do need to go to single-ended for most circuits. So typically when you leave the IC chip, if your chip is, for example, an op-amp, you may have several differential amplifiers cascaded like this, linked together. So you can use the differential outputs, you can maximize your gain at each stage. You can have a differential input, but at some point you're probably going to need a single-ended output, okay? So how do we do that? Two common approaches. One is simply by ignoring one side, okay? So that's the circuit on the left here. We can just forget the current in this side and we just take the single-ended output. So we discussed that a little bit at the beginning of the MOSFETs, but we don't maximize our gain that way, okay? That will lead to a gain loss by a factor of 2, so 6 decibels loss in gain. But it's a possible approach, so you just completely get rid of this current, don't worry about it. A better way is to use this active load situation. So in here we have a couple of extra transistors which act as a current mirror. So that's a circuit that we're going to play around with in the second or third lab of differential amplifiers, where essentially we can use this current and add it to our V out on one side, so we still get the total current and that we would have got through the differential, just by mirroring it using this circuit. So you'll play around with that in the lab to learn a little bit more about it. You can step through what would happen to the currents here if you're interested to try to work it out, but we won't go through it in detail today. But essentially in the common mode, it will make no difference. It will just have the current flowing the same way, whereas in the differential mode, it will add the currents and you'll get double the current at the output, V out, okay? Okay, so that's it for today's lecture, but just to go over a few upcoming assessment tasks. give you fair warning. You've all got the weekly schedule, so you can see all these things on there, but I just want to remind people. So assignment 2 will be online by the end of the week. Submission deadline is 15th, so you have just over 2 weeks to do assignment 2. That's all going to be on differential amplifiers, okay? So you've had the lectures on these. I'll be adding a few more videos. Of course, use the book as well. But yeah, work your way through that assignment. Try not to leave it to the last minute. You have 2 more, some of you have 3 differential amplifier labs. Some of you already did the one yesterday. First one's going to be all simulation. The next 2 will have a little bit of simulation and a bit of circuit building. My experience is the circuit building takes people a long time because there's lots of little bugs, right? So that first lab is perfect to get you really up to speed at LT Spice. Those second and third lab, don't spend too long on simulation. You should really know how to use the programs by then. The pre-lab will cover some of it too. But yeah, really focus on getting the circuit built quickly because I know simple mistakes can take a long time to debug. And another tip I have there is build it in sub-circuits, all right? To build a part, test that sub-circuit works how you want to. You can also simulate the sub-circuit. You can cut off the other bit, see how that should react, make sure things are working. Because if you straight away go in with 6 transistors, something's going to go wrong, okay? There's a lot of contacts to get right. And please don't forget the differential amplifiers have a lab report. So these 3 differential amplifier labs, you'll be writing a small report, which you can do over the session break. The deadline is the 7th of October. So make that professional, make that interesting. I think it's just a 3-page limit, so it's quite short. But you could put some good figures in there. Don't waste space. Right? Make it concise, professional, and interesting. I have to read 90 of them. I'll be marking one of them. So if I read 90 of the exact same thing, it's really boring. All right? So try to add your own edge to it. Try to make some interesting points here and there. Don't just say, this is what I did in the lab. This is the output. All right? Make it a bit more fun than that. All right? All right, so good luck with that, and I'll see you all, well, a lot of you in the lab tomorrow and next week.
I'm up there already. Are you an environmental science student or?
Yeah.
Yes. Jesus, that's annoying, isn't it? There's lots of students that are actually all different faculties.
Oh, really?
Yeah, yeah.
This is a whole unit for me because I do climate science.
Ah, I met a guy who did his masters on that.
Oh, wow.
Yeah, like climate.
Like atmospheric science.
Oh, you do atmospheric science, do you?
Yeah, so I do climate science. Climate science is my major, but it basically involves atmospheric science.
So you're into like meteorology and you don't meet many people that are like into meteorology or anything like that.
It's weird because they're very. It's because it's such a specific field. It's very hard to find people who actually study that sort of science. It's very.
So this is your undergraduate. Are you going to do a master's?
I'm going to do a master's eventually.
Are you going to go for BOM? Are you going to go and work for BOM? Or
Yes.
one of my old bosses is actually a director at BOM, Mohsen Havez. I actually worked for the International Centre of Food Security at Charles Sturt University.
Oh my god.
Yeah. Oh, I just digitise stuff. And he was the director, but he's now one of the directors in BOM. I think he's still with BOM.
That's amazing.
Yeah.
I know a few from there because I've went to the graduate seminars and then I've also connected with them when I've done like little workshops here and there.
Mm.
So I know Agata Adonska and then I know Andrew Gisson and Andrew Watkins.
Yeah, okay. No, I don't know.
Some of them are like,
I don't know a lot of. One of my girlfriends, Jacqueline Watt, she was a hydrologist, and then she's now become a lawyer. So, we worked in water, but we've all gone off. One of my mates who we worked with there, he's an NRAR, National Resource Authority regulator. He just posted something. Actually, it was so interesting. $88,000 fine issued. There's been changes in no changes in the legislation, but changes in the way in which they manage people and what they do in relation to activities on waterfront land. And they've started to fine people for realigning creeks or doing illegal rock work and stuff like that. Yeah, and it's not going down. They're not real happy, a lot of people. So, but he just published next week his water management. And I was like, yes, because it was the largest fine ever issued. 88,000. Yeah, the guy actually realigned a creek. Sadly, actually, if he had got approval.
He changed the entire structure of the creek.
Yeah. I think he might have been a wealthy man. He thought he needed to have a pretty creek on his property or something. Anyway, so, and he just posted that on social media, and I'm going to download that entire story because it's going to be featured in our lecture next week. Yeah. Just because it shows, like these are things that we all think we just do these things just cause. It's actually a legal reason. So have you read the assignment yet or anything?
Yeah, we went through it in the practicals.
Are you external?
I'm internal.
Okay. Were you in that prac I just did?
No. I'm the Thursday practicals at 9 to 11. There's two practicals. There's one on a Wednesday, which is this afternoon,
Yeah.
and then there's one on a Thursday, which is from 9 to 11.
Oh. Okay. So somebody already went through the REF assignment with you?
Emily did last assignment, so she did a general outline, so she introduced us to the assignment, what's involved, how we're incorporating what we've done throughout the week.
Yeah, yeah.
And then she said that in this lecture, you'd be going through it in a bit more detail as to what's involved and how we actually, with group assignments as well, because apparently you put us with different people, you create the groups for us.
Yeah, I did. Some people are not very happy about that, but it's really good for, in the real world, we don't get to choose who we work with. Yeah. So we don't, you know, we need people to be able to work in departments and work together, but we also need them to be able to not work with their friends.
So I'm doing that in a placement at the moment.
Are you? Yeah, and how's that going?
It's really good.
Yeah.
It's actually really interesting. So I'm doing air quality in New South Wales with the dust storms that happened in February this year,
Oh, yeah,
the 11th to the 15th.
yes.
So we're doing
Yeah, we're pretty bad in regards to who, aren't we? World Health Authority?
what,
Who?
Office of Environmental Heritage, OEH.
I did a noise and air policy for the West Council, and part of it was researching for air. And so we had to have international standards and for air quality. When you look at WHO, it's called WHO, World Health Authority. So
I'm
the,
surprised though.
yeah, it's not quite good.
I know that because I live in South West Sydney, so because I'm in a dip, I get quite a the secondary source from the highlands, so it kind of sits there for quite a bit.
That's just pretty bad, and we're quite good at getting rid of our soils because dust is a soil.
Yeah, that's what I said because the stuff that's picked up from Central Australia and brought over here is extremely fertile.
It's called low acid clay, or Hana,
Yeah.
and it's high in iron, and it is really fertile. But the problem is that the soil is void of